Hi, everybody. Welcome back. Lecture 18 is our first lecture where we are going to go through the entire hypothesis testing procedure. In particular, we are going to be working on hypothesis tests where the population standard deviation is being provided to us. That is going to change in the lecture after this one, and it's going to change the process a little bit. So when you're reading the words of the problem, be on the lookout for whether or not you have the population standard deviation. In all of the work we do today, we are going to be given the population standard deviation. What you'll learn today, there are several types of hypothesis tests that can be performed on sample data. We will conduct hypothesis tests in which the claim is about a population mean. In the examples we practice in this lecture, we will be provided with a population standard deviation, and our probabilities will be calculated from normally distributed sampling distributions. So this is a normally distributed sampling distribution. In the next lecture, we are going to be shown problems without the population standard deviation, in which case we follow a different process. So basically, I'm going to walk us through three hypothesis tests from beginning to end, and hopefully by the last one, you'll have a good handle on how to do these. Blood pressure monitors example. A healthcare manufacturer claims that its new blood pressure monitoring device reports a mean systolic reading of 120 under controlled conditions with a population standard deviation of 4. A group of medical researchers suspects the device tends to report higher readings than advertised. They test 50 devices and find a sample mean of 121. Is there evidence at the 5% significance level to support the researchers' suspicion that the device reports higher systolic readings than 120? Okay, so we see some hints as to the direction in these underlined phrases. Um, the medical researchers have a suspicion that these devices are giving higher readings, and down here we see higher than 120. So this gives us an indication that we're working with a sample, or that we will be working with a sample that is on the right side of center, because we're looking at higher than what is considered to be average, the 120. So important details that we get out of reading this problem. We get that the current established population mean is 120. That is our mu. We also get, by these phrases here and here, we also get that the counterclaim is that the population mean is greater than or more than 120. That helps us with the direction. So when we build our null and alternative hypotheses, we are going to make use of the direction. More specifically, when we write our alternative hypothesis, we are going to make use of the direction. The null hypothesis, we never indicate that there is a difference between the current established population mean and what this group is attempting to test. This group of medical researchers is attempting to test um, to see if there's a higher average. So in the null hypothesis, we're going to state that the population mean systolic blood pressure reading of the blood pressure monitors is 120. We're making the assumption that the monitors say they do what they say. They have a mean of 120. And that's the assumption. we write symbols, mu equals 120. So symbolically, our null hypothesis is expressed as mu equal 120. Now, it's in the alternative hypothesis where we state the direction and the counterclaim. The population mean systolic blood pressure reading of the blood pressure monitors is more than 120. So this is the counterclaim that the medical researchers put forward. And so the symbols mu greater than 120. Okay, so is 120 in the null hypothesis and is more than 120 in the alternative hypothesis. Equals in the null hypothesis, greater than in the alternative hypothesis. That was step one, writing our null hypothesis and our alternative hypotheses in words and in symbols. The distribution that we're going to specify here depends on its what we were provided with in the problem. When we calculate our p-value in this problem, we are going to determine if our sample result is rare, because our p-value is a determination of how rare the event is. To calculate the p-value, we need to know which distribution to use. So that's why step 2 is really important. When the population standard deviation is provided and n is greater than 30, we're going to be using the normal distribution. If the sample standard deviation is provided instead of the population standard deviation, we're going to be using the t-distribution. We're not going to be doing that this lecture. That will be our next lecture. This lecture, we're always going to be provided with a population standard deviation. N is going to be greater than 30. We are going to use the normal distribution. Okay, and that's going to be the case in the other examples I do in this lecture as well. So step 3, label the picture of the distribution, including the mean, that's the center, the level of significance, and shaded critical region and labeled conclusions. So by that, I mean we're going to have our picture of our normal distribution. In the center, we're going to label the mean of the sampling distribution. Mu sub x bar is 120. And the level of significance in this problem was given at 5%. The critical region is the shaded region in the level of significance. It's right here. Now, why is the level of significance on the right-hand side instead of the left-hand side? That all is determined by the alternative hypothesis. Going back to the alternative hypothesis, let me go back. Where is it? Here. Going back to the alternative hypothesis, the counterclaim is that the blood pressure readings are more than 120. And because of the phrase more than, we're going to be shading the critical region in our picture on the right-hand side. More than, greater than. So we shade our significance level, which is 5%. We shade the top 5% of the curve. And this top 5% is considered the critical region. Any sample result that falls in that critical region is going to end up with a conclusion to reject the null hypothesis. Because if it falls in this critical region, that means that the p-value, the probability of the event happening, and let me try and change my color here. Let's say I had an X bar that falls right here. If the p-value is calculated for that X bar, you see it's that shaded area in blue. It's smaller than alpha. And when that happens, we reject the null hypothesis. And let me remove that blue because I don't want the blue anymore. Let's get rid of. But it's also possible that we do this test and we don't get a significant result. It's possible that instead of getting a result in the critical region, we get a result in the non-critical region, which is to the left of this vertical line right here. So if I got an X bar over here, for example, that would indicate that my p-value, it would be the area to the right of this line, that p-value is more than alpha, and that's going to result in a conclusion to fail to reject the null hypothesis. So our step 3 is all about setting up our picture, getting ready to receive the results. We don't yet know the results. We're just preparing for the scenarios that could happen. We're preparing for a scenario where we fail to reject the null hypothesis, and we're preparing for a scenario where we reject the null hypothesis, and the picture helps us understand when we will get those kinds of conclusions. Step 4, we're going to write a decision rule. This decision rule tells us how we will reject the null hypothesis. So here's that picture again, this very important picture, and rejecting the null hypothesis is on this side, and we can reject the null hypothesis if our p-value, when we calculate it, comes out to be less than alpha. So we're going to write that. Reject the null hypothesis, reject HO, and accept HA. That's a conclusion. There's only 2 types of conclusions. I went over in the last lecture. This is the type of conclusion where you reject the null hypothesis. Reject HO and accept HA at a significance level of 5% if the p-value of the sample statistic is less than or equal to 0.05. So our p-value could end up smaller than 0.05. It could end up bigger than 0.05. If it's smaller than 0.05, our decision rule tells us reject the null hypothesis and accept the alternative. So now we're going to step 5. We're going to actually look at our data and calculate the p-value. We have something even better than normal CDF to do this. We have a function on the calculator called z-test, and it works on all TI-84s. And we're going to use the z-test to find our p-value. We are going to identify the symbol and the value of the sample statistic as well. So to start, we go to our calculator's z-test function. Let me go to the calculator with you. Okay, so we're going to press stat, and we're going to go to tests, which we have not done before, and we're going to go to z-test. Z-test has 2 types of input at the top, data and stats. For this problem, we're going to highlight stats and hit enter on it. It's already by default there. If we were entering raw data, if we were provided with raw data and needed to enter the raw data into the calculator to calculate the p-value, we'd click data. Without the raw data, we have the statistics. They were provided to us in the problem. Mu sub 0 represents the population mean as stated in the null hypothesis. And in this null hypothesis, it was the blood pressure population mean 120. The standard deviation provided to us in the problem is also expected here. You're going to enter 4. Just double check that that was it. Yep, it was 4. Okay. The X bar provided in the problem, when the group of medical researchers collected their 50 devices, they found the sample mean to be 121. So we're going to put this here, 121. And they did that with 50 devices. So we're going to put 50 here. This is our sample size. The next line, you indicate the direction of your test. When it's a test on the left, you choose less than mu sub 0. Remember up here, mu sub 0 is 120. If your alternative hypothesis states that mu is less than 120, you would choose the less than mu sub 0. Since our alternative hypothesis states that mu is greater than 120, we're going to choose the greater than mu sub 0. Because mu sub 0 is 120, we're going to choose greater than 120, greater than mu sub 0. The other type of test, I referred to it in the previous lecture, is a bidirectional test. I don't have any problems like that I'm going to be doing with you this semester, but when you see a problem like that, if ever you take another statistics class or you do this your in your work, you're going to be using a not equal mu sub 0 in this z-test function. The color is optional, just you change it if you like, and then you hit calculate. We did have an option. I'm going to back up, do that again. Stat, tests, z-test. Sometimes it's unpredictable what drawing will come out with. I'm going to press draw and see what happens. Okay, that's nice. It draws us our standard normal distribution, and it shades a piece of area on the right-hand side. Why on the right? Because when we specified our direction, we said greater than mu sub 0. The p-value that comes out is down here, 0.0385. Now, if I didn't choose draw and I chose the other version, let's do that again. Z-test. If I just chose calculate instead of draw, I would get the details but no visual. So I see a z-score. I'm not going to be using the z-score, although some people do use a z-score to make their conclusion. We're going to be just taking the p-value, 0.0385, 4 decimals for the p-value. And x bar equal 121 is just a restatement of the sample mean and a restatement here of the sample size. It is nice to see the visual though. So hitting draw was useful. And maybe I'm going to be doing that for the next 2 examples after this one, because I do like the way that comes out. So it also rounds our p-value for us, which is nice. P equals 0.0385. The z-score is helpful for determining the location of this vertical line right here. That is the z-score. I'm not going to be using it in making the decisions, but it can be used in hypothesis testing if you have critical z-scores that you are comparing it to. But I like to use p-values and compare my p-values to a level of significance, which is alpha. So let's go back to the slideshow now. Okay, so our answer here, a p-value of 0.0385. I'm going to be asking you for the value and symbol of the sample statistic. The symbol of the sample statistic is X bar. Its value is 121. The calculator didn't need to give this to us. This was given to us in the original problem, but I do want you to state it so that I know that you know what it is. And the p-value of that sample statistic is 0.0385. That is the area to the right of 121. Okay, you're going to be providing all this information when you do the homework assignment for lecture 17 and also when you take the final exam. Step 6, your conclusion. So to make a conclusion, it's very helpful to go back to the picture. So we're going to go back to our diagram where we had alpha labeled at 5%, and we're going to Identify the p-value on this same diagram. The p-value was 0.0385. And the reason why I drew it up here in this blue shaded area is because it is less than 0.05. Therefore, it needs to sit to the right. X bar must be to the right of this vertical line. This is the highest 3.85% of area. And because that is smaller than 5%, I make it on the top right here. And I put X bar, in this case, inside the critical region, the reject HO critical region. And that helps us make our conclusion. Now we know that X bar is on the inside of the critical region. We can reject the null hypothesis. So our official conclusion is reject HO and accept HA at alpha equal 5%. And we're doing this because our p-value is smaller than 0.05. If our p-value is smaller than alpha, we can reject the null hypothesis and accept the alternative hypothesis. This is what the medical researchers believed was true, and that's what we stated in the alternative hypothesis, that the mean blood pressure reading was greater than 120, and our sample mean gave us a value that was statistically significant. Okay, the sample result is considered statistically significant. A general rule on conclusions: when making a conclusion, you're going to be comparing the p-value to alpha. Sometimes the test will be on the left-hand side, like in this example, and sometimes the test will be on the right-hand side, like in this example. It all depends on the alternative hypothesis. No matter what side the test is on, your p-value still needs to be smaller than alpha in order to reject the null hypothesis. So notice in both these cases, the p-value is a smaller piece of area than alpha is, and that's why we are rejecting the null hypothesis. If the p-value is less than alpha, the conclusion is reject the null hypothesis and accept the alternative. And that will always be the case no matter if the test is on the right or the left. Now imagine other scenarios. Imagine a scenario where you got a blood pressure average, and remember mean is 120. But imagine you got a blood pressure average in your sample that wasn't as far over as the X bar that we did get. Let's say it was 120, maybe 0.5. Okay, well, that's not considered to be significant because it's not to the right of the vertical line. I'm putting it out here intentionally because I want to show you that sometimes you do end up with a sample mean that is still greater than the population mean. 120.5 is greater than 120, but it's not great enough. It's not significant enough. It is an increase, but it's not a significant increase, which is what we got when we got an X bar of 121. And then when that happens, that's when we fail to reject the null hypothesis. Okay, but going back to this particular test, because we did reject the null hypothesis, the answer to the question, is there evidence at the 5% significance level to support the researcher's suspicion that the device reports higher systolic readings than 120? We say yes. The sample data supports the researcher's suspicion that the device reports higher systolic readings than 120. Give me a second. Is there evidence that the devices report higher systolic readings than 120? Yes, the sample data supports the researcher's suspicion that the device reports higher systolic readings than 120. The device gives readings that are significantly higher than the manufacturer reports. So you really don't know the answer to a question until you really get to the end and look at the p-value. You can take guesses and make assumptions, but nothing is as clear as looking at the p-value and comparing that p-value to alpha to give you your final conclusion. So there are 7 steps to the hypothesis testing procedure. We just finished step 7. So I'm going to take you through another question now. And it's got slight variations. So we see different types of scenarios. Hospital discharge time example. A hospital administrator claims that the population mean discharge time for patients after routine surgeries is 5 hours with a population standard deviation of 1 hour. A group of patients believes that the actual discharge time is less than 5 hours on average. To test this claim, the group records the discharge times of 36 randomly selected patients and finds a sample mean discharge time of 4.7 hours. Does the sample result indicate that the hospital's discharge time is less than the claimed mean of 5 hours? Use an alpha, a significance level of 0.01, which is 1%. So I highlight in bold, you see the important information, and it's not always going to be like that. You're going to be responsible for extracting this information from each problem that you have to do. The important details here is that we have a current established belief and understanding that the population mean is 5 hours. And the counterclaim is that it's less than 5 hours. The group thinks that the discharge time is less than 5 hours. Okay, so knowing that we have a less than in the counterclaim means that this test is going to be on the left-hand side. And we're going to write up our alternative hypothesis to show that. First, the null hypothesis. The population mean discharge time for patients after routine surgeries is 5 hours. So we don't state any direction, we just state that it is 5 hours. Mu equals 5. And now our counterclaim, the population mean discharge time for patients after routine surgeries is less than 5. So our counterclaim in the alternative hypothesis always specifies a direction. Mu less than 5. So this direction, less than, influences what our picture looks like, and it influences how we calculate the p-value when we eventually go to our calculator. The distribution, either normal or t-distribution, and we've not yet seen a t-distribution question. Today, they're all normal distribution questions. The reason why it's a normal distribution is because the population standard deviation was provided and n was greater than 30. We're going to use the normal distribution. Next, we're going to build our picture. Our picture puts our mean in the center, and that's going to be the mean of the sampling distribution. It's going to indicate the level of significance, which was, I think, 5%, and it's going to be on the left-hand side. The critical region is going to be shaded in, and it's going to be on the left-hand side. And across the top, we're going to label the conclusions, reject HO, and fail to reject HO. So here's our mean of the sampling distribution in the very center. We shade the bottommost. Oh, I was wrong about the significance level. Let me see. Go back to the words of the problem. The problem said, okay, 0.01. I was wrong about the significance level. It is 0.01, 1%. Okay. So we shade the bottommost 1%, the leftmost 1% of the curve. That is our critical region. Any p-value within that critical region will give us reason to reject the null hypothesis. Any p-value outside of that critical region, we will fail to reject the null hypothesis. So we're looking for a p-value that is smaller than 0.01. So let's write that in a decision rule now. How we will reject the null hypothesis. We will reject the null hypothesis and accept the alternative at 1% if the p-value of the sample statistic is less than or equal to 0.01. This is our guiding rule. This is what we come back to. When we get our p-value, we can come back to our decision rule and we can check, is it less than or equal to 0.01, or is it greater than 0.01? And that will help us make our final conclusion. So we're going to go to the z-test on our calculator now, and we're going to calculate the p-value of the sample statistic. So let's open up z-test. I'll do this with you. Okay, we're going to do stat tests, z-test number 1. Make sure we're highlighting stats again. Only highlight data if you're provided with raw data. The mean was 5. The standard deviation provided was 1. The x-bar provided in this problem is 4.7 and n 36. The direction, less than. And I do like what draw did for us last time, so I'm going to do that again, and we can get our p-value and look at the picture. Okay, so we get a p-value of 0.0359, and you can see it's being shaded on the left-hand side. So we get a p-value of 0.0359. Our sample statistic symbol is x-bar. Its value is 4.7. That comes from the original problem, but the p-value comes from z-test, 0.0359. So now we can make a conclusion by comparing our p-value to alpha. Let's go back to the picture that we made for our decision rule, where our alpha was 0.01, and recognize that the p-value of 0.0359 is bigger than 0.01. Okay, it's a bigger area than 0.01. So therefore, I make it outside of the critical region. I make the p-value bigger than the critical region. And on the border of that p-value is x-bar of 4.7. So while it's true that the sample mean was less than 5, it's not considered to be significantly less than 5. For it to be considered significantly less than 5, we would have needed that x-bar to be past this vertical line here and into the critical region. And we know it's not in the critical region because the p-value is bigger than alpha. Okay, so we have a conclusion here, and it's going to be fail to reject the null hypothesis. The p-value is not smaller than 0.01. The conclusion is fail to reject HO at alpha equal 1%. This is one of those situations where this p-value is truly a significant p-value if we were working with a significance level of 5%. But since we're working with a significance level of 1%, and that's always provided to you in the problem, which significance level you're using, this p-value turns out to, it turns out we have to fail to reject the null hypothesis because it's not considered significant enough. So, does this sample result indicate that the hospital's discharge time is less than the claimed mean of 5 hours? And so, since we were using an alpha of 1%, we have to say no. The sample result does not indicate that the hospital's discharge time is less than 5 hours. It's not. The discharge times are not significantly less than 5 hours claimed by the hospital administrator. So you can see how different alphas can really change the way a conclusion ends a hypothesis test. Sometimes the alpha will be 5, sometimes it will be 1, and depending on what the p-value comes out to be, you can fail to reject or reject. So it's something that we don't know ahead of time, but we see it when we get to the final steps where we have to calculate the p-value. The last problem we're going to do is about medication dosage consistency. A pharmaceutical company claims that the population mean active ingredient content in its pills is 10 milligrams, with a population standard deviation of 0.5 milligrams. Okay, so we have a population mean and we have a population standard deviation. And now we have another point of view. The production manager suspects that the pills actually contain more than 10 milligrams on average. If the production manager tests a random sample of 40 pills and finds the sample mean content of 10.2 milligrams, can the company's claim of 10 milligrams per pill be refuted? Use a significance level of 1%. So our alpha this time is 1%. Okay, so at first glance, 10.2 doesn't seem to be a lot more than 10. So you could make an assumption that there's not enough evidence there, but you never know until you look at the p-value if that's 10.2 is considered significant or not. So let's start the test. Important details that we want to pull out of here. We want to pull out that the current established mean is 10. That's going to be used in our HO. And we also recognize that the counterclaim is more than 10 counterclaim, and that's going to be used in our formulation of HA. So let's write HO and HA out. HO, the population mean active ingredient content in the pills is 10 milligrams. Mu equals 10 is the symbols. And HA, the population mean active ingredient content in the pills is more than 10 milligrams, mu greater than 10. Okay, so we have our HO, we have our HA. The direction tells us the greater than sign in HA tells us that the direction will be on the right. And so we're going to be working with an alpha on the right-hand side and a p-value that extends to positive infinity. So we're working up here. Identify the distribution. You will be asked on tests and homework, is it a normal distribution or is it a t-distribution? In which case because you have the population standard deviation and n is greater than 30, you're using the normal distribution. Population standard deviation is given, and n is greater than 30. Sometimes the problem will use symbols instead of the word population standard deviation. So just recognize that if the problem provides you with sigma, that is the population standard deviation. Okay, let's build our picture, labeling the significant region, the critical region on the right-hand side, and the mean in the center. So 10 milligrams for the content in the pills is in the center, the mean of our sampling distribution. On the right-hand side, we shade the topmost 1% for the critical region. Any test result that ends in the critical region, we will be able to reject the null hypothesis. Any test result that falls out of that critical region, we will fail to reject the null hypothesis. So let's write out the decision rule in words then. You will reject the null hypothesis and accept the alternative hypothesis at alpha equal 1% if the p-value of the sample statistic is less than or equal to 0.01. Okay, so it doesn't matter that this test is on the right. We still want a p-value to be less than 0.01 because in order to reject the null hypothesis, in order for our test result to be significant, we need to have an X bar that is significantly further to the right of 10, which is going to result in a p-value that is smaller than 0.01. We need it past this vertical line. So we go to z-test on the calculator. I'm going to do this with you. Okay. So let's go back to stat, tests, z-test, and we're going to enter in 10 from u sub 0. That's the population mean. 0.5 for the standard deviation of the population, and 10.2 for the sample mean. The size of our sample was 40. It's a test on the right-hand side, so we're saying here in our alternative hypothesis that mu is greater than 10, and we'll go and draw that. Okay, and you can see that the area is really small on the top right of the curve here, and its p-value is coming out as 0.0057. Okay, 0.0057. Also, if we do z-test using just the calculate feature, it gives us the same p-value, of course. So our sample statistic, its symbol is X bar, its value is 10.2 from the words of the problem, but the p-value we just got 0.0057. So that's a really rare event. That's a very small probability. Compared to 1%, it is smaller than 1%. So look at 1% is 0.01. 0.0057 is smaller than 1%. So when we look at our picture, 1% is this piece of area. Our p-value is smaller than that. It's even smaller than 1%. So I draw this X bar inside the critical region to show that the p-value is smaller than 1%. And because it's in the critical region, we reject the null hypothesis and accept the alternative. We reject that the population mean is 10, and we accept that it's greater than 10. Accept the alternative. Okay, we make our conclusion now. Formally, we state that we reject the null hypothesis and accept the alternative hypothesis at 1%. So this is the formal conclusion. Now, we always want to answer a final question because it actually puts meaning to the problem. What does it mean to reject the null hypothesis and accept the alternative hypothesis? Who's correct? Is it the pill manufacturer or, let's see, who's the company claim that, yeah, the pill manufacturer claimed it was 10, and then the manager believed it was more than 10. Do we have enough evidence to refute what the company was saying? And the answer is yes. The company's claim of 10% of 10 milligrams per pill can be refuted. We can accept that the mean is more than 10.2. So it's the manager who is correct here. The active ingredient content is significantly more than 10 milligrams claimed by the pharmaceutical company. And that is the end of our lecture. So we did 3 full-length hypothesis tests from beginning to end. So it's not just about getting the p-value, but you do want to do all the setup. You want to get good at setting up the test, writing a decision rule, making a picture, um, stating your hypotheses. And then in the end, you do want to be able to answer a question. It is sometimes for some students, it may be the most challenging part, answering the final question in the hypothesis test. So you do have homework that asks you to do all these things. And if you just get the p-value alone, you're not going to get much points on that or on a test. So you want to make sure you can do all the steps. I hope that was helpful. If you have any questions, please email me and I'll see you at the next lecture.